start the session.
Okay, a very good evening to all of you. So I'll present on geothermal energy future trend. This is very basic presentation. I'll start from the fundamental things, and this presentation will include introduction about geothermal energy. I think I'm audible, right? My voice is clear?
Yeah, ma'am, pretty well.
Okay. So let me know if I am disconnected, please let me know. This is the outline of my presentation: introduction, prospects, exploration process flow, case studies. Along with the exploration process, I will discuss different case studies worldwide and from India, future trend, summary, and conclusion. So as you know, geo means earth and thermo, which means heat. So geothermal energy, this is the internal heat of earth. It is a clean and sustainable source of energy. Geothermal resources are found in different temperature ranges from low to high enthalpy resources. This geothermal energy has been providing commercial electricity from conventional hydrocarbon resources as well as unconventional geothermal resources since 100 years, more than 100 years. If we talk about conventional geothermal resources, then high temperature systems which are greater than 225 degrees Celsius and that can be present at less than 2 kilometer depth. It is simply the heat energy generated from the earth, which may be the energy which was generated during the planet formation and which has not yet been lost. Then due to decay of radioactive elements due to frictions, and geothermal reservoirs we can found in different areas like geysers, boiling mud pot, then volcano hot springs. Here in this image B, this image is indicating how the hot streams and waters are coming upwards, and this porous and permeable zone is acting as reservoirs. And from this zone, we can extract energy using, if it is at shallow depth, then we can use conventional techniques. If it is at higher depth, then we have to go for unconventional advanced techniques. So geothermal energy system, there may be different types of geothermal systems like water dominated and vapor dominated. First one is vapor dominated, and then liquid dominated or water dominated. These are different examples. Here you can see mud pots and springs. It may be silica dominated, or you can get springs in carbonate depositional systems also. Silica dominated springs with a significant runoff silica deposits known as siliceous sinter indicate subsurface temperatures above about 210 degrees Celsius. This is just overview about geothermal energy, how it is playing important role in electricity, fulfilling the electricity demand. More than 74% electricity generation. You can see this is for 2020. This graph is showing how it is playing very important role, and it has more role than wood-based, other biomass-based, hydroelectric, solar, and wind-based electricity generation. These two graphs are showing energy demand trend up to 2030. And this is the combined demand for up to 2030, including wind, solar, geothermal. And all of you know how to calculate geothermal gradient. As with increasing depth, normal geothermal gradient increases, and this geothermal gradient may vary from place to place depending upon various factors. It depends on type of rocks found in that area, thermal properties of the rock, presence of underground water reservoirs, age of the rock, igneous activity under that region. So here, this is normal, this trend is showing normal geothermal gradient 20 degrees Celsius per kilometer. If we go through this trend, then this is the zone where you can get hot sedimentary aquifer after 2.5 kilometer or 3,000 kilometer. 3,000 meter, 3 kilometer depth, we can get hot water aquifer, and after that oil and gas deposits we can found. But if geothermal gradient is 50 degrees Celsius per kilometer, high geothermal gradient, then at shallow depth also we can get hot springs and geothermal energy, which can be used for direct electricity purpose or any commercial purpose. We can use that. If the geothermal gradient is very high, which is more than 100 degrees Celsius per kilometer, then at very shallow depth, we can get conventional geothermal resources or deposits. For this, flash is one technique which power plant, flash plant, we can use to extract those resources. Then binary is generally used for other resources which are at higher depth. In case of conventional, we can get, as I have already told, that at shallow depth, high temperature zones are present at shallow depth, which is less than 2 kilometers. We can get more than 200 degrees Celsius temperature. And for unconventional geothermal resources, these are very common in most of the areas worldwide, but depth is high, so we have to go for unconventional techniques to explore these resources. So classification of geothermal systems: superficial, hydrothermal, and deep petrothermal. So two types of deep geothermal resources from which electricity can be produced. That two are hydrothermal and petrothermal. Hydrothermal resources have naturally occurring geothermal fluids at depth. It is often generated from surface infiltration of precipitation, and the fluids can be used as heat carrier, and it can be taken out from the ground through boreholes. Then how to generate? This is the injection well. As water is pumped through an injection well, it passes through the cracks on the rocks and then comes back up again through the recovery well towards the surface. Due to high pressure, water is transformed into steam while getting to the surface. This is a heat exchanger. This stream is passed slowly to heat exchanger and then transferred even into further turbine. Then it can help in generating the electricity. So three types of geothermal plants: dry stream power plant, flash stream power plant, then binary cycle power plant. You can see different temperature ranges, and these temperature ranges where we will get the high temperature zone and where we will get low temperature or intermediate temperature, that is completely depend on the locations. Generally, boundaries of tectonic plates on hot spots and volcanic areas, we can get higher temperature. And for this high temperature at shallow zone, we can use flash and dry stream power plant. Now, what is dry stream power plant? Dry stream geothermal resources are rare and only available in few regions, including the geysers in California. Here, the stream is piped directly from underground wells to the power plant, where it is directed into a turbine generator unit that produces electricity. In case of flash stream power plant, this uses geothermal water with temperature greater than 180 degrees Celsius to 182 degrees Celsius. Hot water flows up through the well in the underground, in the ground under its own pressure. As it flows upward, the pressure decreases and some of the heat water boils into steam. The steam is then separated from the water and it is used to power the turbine or generator. Any leftover condensed water or steam are injected back to the reservoir and which can be used as the sustainable resource. Then binary cycle power plant, which is commonly used because most of the geothermal resources are present at a higher depth. So this is low to moderately heated below 400 degree Fahrenheit geothermal fluid, and secondary binary fluid is present here. Here where the binary fluid with a much lower boiling point than the water passes through the heat exchangers, and heat from the geothermal fluid causes the secondary fluid to flash to vapor, which then drives the turbines, and then subsequently it flows to the generators. As I told you, global distribution of geothermal resources are completely dependent on geological settings. Geothermal plays in relation to plate tectonic settings. Plate movements, and their positions are very important to identify the locations for geothermal resources. Other than this, petrophysical properties also play a very important role. Then permeability structures, geological structures, fluid chemistry. These are the very important factor for geochemical resource exploration. Here, this red line is showing plate boundaries, divergent plate boundary, mid-oceanic ridges transected by transform faults. Then transform fault, you can see this blue line is showing the transform fault strike slip zone. And here you can see there are different examples for geothermal fields, Topo, New Zealand, Kamajang from Indonesia, then Reykjavik from Iceland. These are magmatic volcanic field. Then magmatic plutonic types includes Lardorello, the geysers. Then extensional domain types of it. There are lots of examples with respect to different plate boundary positions. And major geothermal fields are present in circum-Pacific margins, rift zone, East Africa, North Africa, and basins of Europe, Asia to Pacific. Are include Sunda basins, including Salton, Taft, Gulf of California. Then amagmatic rifts include Iceland, East Africa rift. These are the major zones where geothermal prospects are present. And in India also, we have lots of prospect of geothermal energy. With an installed capacity of almost 4,000 megawatt, US is the leading producer of geothermal energy across the world, and it is producing almost 17 billion kilowatt hour, means 16.7 billion kilowatt hours of geothermal energy throughout the year. Most of the geothermal power plants in US are in western states and Hawaii. This include the Northwest Volcanics, Salton, Taft, Northern California Coast Range, Rio Grande Rift, and Colorado Plateau, Hawaii, Alaska. Lithology in most of the provinces is of non-sedimentary type, except for the reservoirs in Salton, Taft, where reservoirs are non-marine deposits with evidence of igneous intrusion, contact metamorphism, and hydrothermal alterations. And in California, the largest known dry steam field is present there, which is producing electricity since 1960. So this image is showing typical geological settings for geothermal systems. In active volcanic geothermal systems, reservoir lithologies are typically igneous rock, andesitic arc, magmatic arc. In amagmatic geothermal system, extensional, here reservoir lithology is typically igneous rock, includes rhyolite, andesite, basalts, plutons, then metamorphosed basements. In continental settings, an amagmatic rift, carbonates, magmatic rocks, which includes karstic, marble, quartzite, schist. Volcanic rocks include basalt and basaltic andesites, plutons, and sedimentary rocks may be there, which may include volcanoclastic materials also. So here red line is indicating, you can see different symbols for springs, fumarole, bicarbonate waters. Here this red arrow is indicating hot fluids, gas and water. These black lines are indicating the well locations. And these are the zones with high permeability. Then structural settings, geological structures play a very important role in geothermal exploration. There may be highly prospective zones which are present in structurally complex zone. So you have to identify, there are different techniques to identify structural positions and different orientation, then nature of faults. In this image, you can see first one is showing fault termination measure. This is the major fault, and here these red zones are indicating the prospective zones for geothermal exploration. And here where you have to drill the well, where you have to define the location for well, that is very important. Before that, you have to understand the geology, subsurface geology of the area. The second one, this is the step over and relay ramp, where the blue color dot is indicating the position, well positions where to drill the well. Then second one, that is the fault interaction. This image is showing displacement transfer zone, where this is very complex faulted zone. And this is the defined zone. Red color is the prospective geothermal zone. Here blue color stars in all images. Blue color stars are indicating the proposed well locations. As porosity and permeability, these two parameters play a very important role in reservoir quality of the geothermal reservoirs. Conventional geothermal resources are typically hosted in reservoir formations that have greater than 10 to the power minus 50 meters for permeability. Then unconventional resources have very low permeability. It varies. Porosity, permeability, these petrophysical properties vary with respect to depth as well as with respect to rock types. You can see here fracture porosity is high along with the permeability. Then porous volcanic and sedimentary rock have highest porosity and high permeability also. Crystalline basement rock has low permeability as well as low porosity. Porosity in current case of carbonate rocks, normal carbonate rock, it is more, but permeability may be less. So you have to understand what type of rock is present there and what are the petrophysical parameters. For this, we need integrated investigation. So what are those investigations that let me discuss. This is the exploration flow chart, exploration stage and exploitation stage. Under exploration stage, regional exploration surveys, then exploitation stage includes field development, field exploitation, energy generation, and commercial distribution. Here we will be discussing about exploration stages only. There are different surveying techniques, including remote sensing, seismic, gravity, magnetic survey, electrical resistivity, magnetotelluric surveys. These are the techniques normally used for geothermal exploration. Collection of different data, identification of active characteristics of study zone, then surface geological evaluation, geothermometry, electrical conductivity analysis, pH analysis, identification of fluid flow from active characteristic zones, soil sampling, and including different geophysical studies. This is one example of geochemical analysis, geochemical mapping, temperature distribution based on geothermometry from Kenya. This geochemical analysis is very important, sampling and anomaly map. This one is showing that this is very important to determine the origin of the fluid, to understand origin of the fluid, to define the chemical characteristics, to estimate subsurface temperatures, and this can provide data towards development of conceptual model for the system, and that model can be applicable for other analogous basins or other analogous prospect. Here, this is the zone which is showing higher temperature. This is higher temperature zone, and this is the prospective zone here. And another map, this one is soil gas survey CO2 distribution. CO2 distribution of Silali geothermal prospective area. In this map, the results are used to produce soil gas survey. This survey is based on presence and ratios of carbon dioxide and thoron gas, radon in soils. This survey measures the concentrations and flux rate of release of these gases. And previous research has shown that CO2 and other gases of magmatic travel to the surface along with faults. So if we know their migration pathways, this is very, we can identify the permeable zones, different geological structures and faults. And this can provide information about chemical and thermal evaluation of the geothermal area. And this method is used in Kenya during the exploration phase and for monitoring of different surface manifestation during the production also. This is geophysical data workflow where raw data, then advanced processing and geophysical assessment. After that, all these geophysical data need to be integrated with geological and geochemical data for resource assessment and well targeting to identify the exact location for the drilling. This data includes magnetotelluric gravity, magnetic, seismic data. Let's discuss some example. This is one example from Newberry Volcano, Oregon. Here, Jones International Industry conducted 2 gravity surveys in the area, Newberry Volcano in Central Oregon for geothermal developer in 2007 and 2010. This survey encountered temperatures from 550 degree, 50 degree, almost 550 degree. Processing and integrated interpretation performed in this zone results that there are more than 100 stations for prospective geothermal exploration. Here, integrated magnetotelluric gravity results. They used the LIDAR technique also. Valuable insight on structural and volcanic, how the volcanic under the subsurface is playing the role, and these data. And this red color is showing the prospective zones where resistivity is very high, resistivity is very low, conductivity is high. So what type of geological technique you will use, that is depend on petrophysical properties as well as the reservoir conditions. For high fluid flow, you will use magnetotelluric. For high temperature, you will use this map is showing this line is the major fault. This black color line is showing major faults, and there are so many minor faults in this geological area. And the dark color zones are showing the intrusives or extrusives sediments. And this is the stratigraphy of this area where I have marked this zone, which is considered as geothermal reservoir. Here, Zestrain, this is the formation. Below that formation, this is the prospective zone for geothermal resource. And this black color line is showing this is gamma ray log. You can see what kind of signature it is coming for the salt rock. And after that, you can see the abrupt change in the lithology. And this is a zone just above the volcanic rocks. This is a zone for prospective geothermal exploration. 3D seismic exploration was carried out in this area across the deep thermal platform that is called Snonebeck north of Berlin. And 2 wells were drilled here up to 4.4 kilometer depth. In this zone, temperature is almost 150 degrees Celsius. So this is the prospective zone identified based on seismic interpretation based on gravity, seismic, and magnetotelluric data. And this table is showing what are the properties they used for seismic acquisition. This one is 3D seismic survey with resources, red stars, red lines are cross lines, and receivers are here in represented in blue line in lines. Blue lines are the inlines, and the horizons in the Rotliegend group and Permo-Carboniferous rock located in subsaline zone below the strain are important for geothermal development that I have already shown you. This is the zone which is prospective for geothermal exploration in this area. So when we talk about geothermal prospect in India, almost more than 400 hot springs are identified by Geological Survey of India, including Himalayan geothermal province, and which can, all these provinces have a lot of prospect for future geothermal energy generation, including all these regions. Himalayan zones, this is the zone. Then Sonata, Godavari Basin, Cambay Basin, and West Coast. These are the zones which are considered as prospective geothermal exploration zone in India. So exploration of geothermal fields was started in 1970 in India. Kuga Valley of Ladakh, it has estimated potential more than 10,000 megawatt potential is there. And other geothermal provinces are Himalayas, Sohana, West Coast, Cambay, Son Narmada Tapi, that is Sonata, and Godavari, then Mahanadi. These are different characteristics and heat flow informations for different localities in India. In Himalaya, geothermal province includes Kuga, Tungtang, Ladakh. Hot springs have 30 to 84 Celsius. This is the temperature. Surface temperature is 160 to 220 degrees. In minus to 96 degrees Celsius, and geothermal gradient more than 100 degrees Celsius per kilometer. Tapovan, this is hot springs of 30 degree to 65 degrees Celsius, flow of 50 LPM to 56. And here the thermal gradient ranges from 44 to 68 degree. If we talk about Son Narmada lineaments, they are also surface temperature 52 degree to 97 degree, and temperature, reservoir temperature, it is up to 200 degree. Then West Coast province, it has also high temperature, reservoir temperature up to 145 degrees Celsius. Then Chotanagpur Naisik complex, this here hot springs temperatures 40 degrees Celsius to 70 degrees Celsius, and reservoir temperature 120 degree to 140 degrees Celsius. In Godavari Valley, hot spring temperatures ranges from 36 degree to 44 degree, and borehole temperature was found 50 to 60 degree. Assam also, there are a lot of Assam and Arunachal, because Arunachal is the foothill of Himalaya, and there is the MBT falls. All these faulted zones are prospective for geothermal exploration. There are a lot of hot springs reported in Jakram in Meghalaya, Garampani in Assam, Takshim in Arunachal Pradesh, and where temperature up to 120 degrees Celsius. So let me talk about what is the current status of geothermal exploration in India. ONGC is installed the first geothermal development project in Ladakh. ONGC will develop India's first geothermal field project in Ladakh. Recently, in February 2021, ONGC Energy Center signed a MOU with Union Territory of Ladakh. And the first, it was started, this drafting was started in 2015, and MNRE launched the draft national policy of geothermal energy, and it was planned to install geothermal energy capacity up to 1,000 megawatt at the initial phase. But in 2016, the policy has changed, And India looks to harness 10 gigawatt geothermal power plant by 2030. So first phase of this pilot project will include 1 megawatt power generation capacity to be installed, then 100% free power to be supplied to the general public. ONGC Energy Center is implementing agency for the pilot project. In the phase 2, deeper and lateral exploration of geothermal reservoir by drilling optimal number of wells will be drilled. Then there will be an installation of higher capacity demo plant in Ladakh. Then for phase 3, this is to be a commercial project as per discovered capacity. Then actually I put one video here, but it is not working, I think. Okay.
एनर्जी के लिए जो बेस्ट एरिया होता है उसका सिलेक्शन बहुत सारे फैक्टर्स पर डिपेंड करता है.
So this is the temperature gradient for Puga Valley. You can see different temperature gradient temperature ranges. It is up to 300 meter depth, and temperature gradient at 300 meter depth, you can get more than 120, almost 130 degrees Celsius temperature. And this image is showing magnetotelluric studies. Here, this is the zone. You can see with high, this is the zone with high conductivity area, and geoelectric section for 2D modeling of data in Puga showing anomalous conductive features at deep related to deep geothermal reservoirs at the depth of 1.5 kilometers. So at 1500 meter, this is the conductive zones in Puga Valley. This is about Cambay Basin. Cambay Basin, this is because of all the fault structures. There are different faulted blocks in the Cambay Basin, and this one is the Cambay Rift. If you see the thermal gradient towards the west direction, towards west, you have the high temperature gradient at shallow depth, and there are some lows, depressions in the southern base part of the basin where there is depth is high and temperature gradient is also high. The second image, this is showing the high gradient anomaly, temperature gradient anomaly maps, and these are the zones near Kathana, Nawagam, Dadhal. These are the areas where you have and Kari field also. There are some high temperature anomalous zones, and these are oil fields, oil and gas fields in Cambay Basin, and there is some lot of abundant wells also, and in future those wells can be studied for future geothermal energy exploration purpose. And this is the contour map, temperature gradient map for Narmada block. Here these are the zones. This red color, this orange color is showing the high temperature gradient zone. This is again gravity map. Black color dots are indicating gravity stations. Red triangle, these are indicating hot springs. Then these are the graphs for Boger anomaly, then residual gravity anomaly. And you can see this is the zone near to hot spring. You can see the variation of gravity anomaly. So magnetotelluric can play a very important role in identifying the hot springs and subsurface geothermal prospects. This is another map, oil field from Cambay Basin, Dholera field. Here, this is you can see depth in meter up to 10 kilometer depth, and this is the zone. Here you can see this is the zone with high conductivity and low resistivity. Here, this is the resistivity distribution of Dholera field. Red color zones are indicating high resistivity, and this blue color zones are indicating low resistivity and high conductivity zones. And this is the hot spring present in this field. So this is one comparison of Piper trilinear diagram showing the hydrogeochemical phases for different water samples collected from Cambay Basin. And the other, these are from Nevada, and this one is from China, prospective zones present in Himalayan geothermal belt. And you can see the variations of here magnesium, then in this side you have chloride, calcium, here sulfate, and you can see the variations of water properties in all those fields, comparison with Nevada. And this one is Gangding field from China, present in Himalayan geothermal belt. These Piper diagrams are very important to understand the water properties as well as hot spring fluid properties, stream properties, to compare their property, and these models can be used for other analogous basins also. So India and other countries have their geothermal prospect in abundant coal mines also. Some of sedimentary basins in India have been found to be moderately high temperatures at sufficient depth, where several wells may be non-flowing or abundant. So in this case, geothermal potential from such wells can be harnessed by traditional two-well systems or single-well systems. And there are different coal fields like Jharia coalfield, Raniganj coalfield, Singareni coalfield, Kolar goldfield, then Mosamani Kolar field mines. You can see the temperature gradient. This is the temperature gradient in Kolar gold mine. You can see. And then Mosamani, that is very high temperature gradient. So we can study, future study can be carried out for geothermal exploration in these fields. Process prospects are present under the subsurface at greater depth. So enhanced geothermal systems are currently being developed and tested in many countries, mainly in France, Australia, Japan, Germany, US, and Switzerland. Then largest enhanced geothermal system project is about 40 megawatt demonstration plant is currently being developed in Cooper Basin, Australia. And this basin has potential to generate more than 5,000 to 10,000 megawatt electricity. So this is the enhanced oil recovery, as like the oil and gas recovery from higher depth, we use hydrofracturing techniques. So here also it requires advanced technique for enhanced geothermal system exploration. And this is a map showing 64 enhanced gas recovery, enhanced geothermal prospective projects around the world. You can see these are the areas where EGS projects are implemented. So although we have lots of prospects, and this is one sustainable clean energy resource, technology is one of the challenges. Successfully locating and drilling geothermal wells is one of the challenges. So it requires integrated technology, integrated geological, geochemical, geophysical, and advanced drilling techniques for identifying as well as extraction of those resources commercially. Then it is difficult to understand how the heterogeneous structures of the subsurface controls the existence of exploitable fluid reservoirs. Another challenge is extreme corrosion, scaling, and thermal stress challenges, and it requires innovations in drilling and well stimulation process. Then there is also issue in induce seismicity. So this is the summary of my presentation. It is clean energy resource. It has a huge prospect, and this release about 1 to 10% of carbon dioxide emissions compared to a fossil fuel plant. And initial investment is high, but once the capital cost is recovered, its price will go down. It will go down below 22.24 rupees per kilowatt. And cost of electricity generation will depend on certain factors, including temperature and depth of the resource, then type of resource, what type of resource is there, stream, liquid, or mix, then available volume of resource, size, and technology of the plant. And lastly, this is the graph which is showing very US geothermal development starting from 1971 to 2019. So these are some references. I can share you these references for further reading. And thank you.